In this slide, we talk about Faraday's law of induction. Essentially, this law is a very important law, and it helps us in actually generation of electricity. And we had kind of introduced earlier a little bit. We said that a change in magnetic flux results in an induced EMF. So this is magnetic flux. And let's just write down a few factors that determine the induced EMF. Induced EMF is directly proportional to the change in flux. That means if the flux changes by a larger amount, it could change because of a change in area of the coil or change in the magnetic field. The larger it changes, the larger is the EMF, or the larger is the voltage induced in the coil. EMF is greatest when the change in time delta t is smallest, and EMF is inversely proportional to delta t. You'll see that in the equation that comes up. And finally, the induced EMF depends on the number of coils that we use. Or for producing larger EMF, you need to have more coils placed in a magnetic field and have the flux change with time. So this is the main formula for calculating induced EMF. And you notice there's a negative sign in front. N denotes the number of coils. We've seen this before. And delta theta is the change in flux, and delta t is the change in time. So what this law is essentially saying is that if we have, say, n coils, I'm just going to draw n such coils, that n of them, and roughly n coils, and if we have the flux changing with time, so delta phi is not 0, I would say is greater than 0, and of course delta t is not 0 because time is changing, then you expect EMF to be induced in the coil, and this will not be 0. If EMF or the voltage across this coil is not 0, then there will be induced current. Now, let's talk about this negative sign. The minus sign in the Faraday's law of induction is very important. It means that the EMF creates an induced current. So this EMF creates an induced current in the coil. So this is the current that gets produced in the coil. And interestingly, this induced current produces induced magnetic field. And this induced magnetic field opposes the change in the flux. So essentially, this phenomenon is called Lenz's law. And the negative sign tells that the induced magnetic flux changes or opposes the change in delta phi. So in this slide, we are looking at an example for conceptually understanding the Lenz's law. So let's look at this top picture on right, and we have a magnet that is moving to the right side, and as it is moving, it is creating a magnetic field shown as B subscript mag, which is the magnetic field produced by the permanent magnet, the bar magnet, which is moving to the right. And there is a coil here shown, and let's say this coil has 3 turns, just for simplicity, 3 turns. And this coil is circular, and what we are saying is when the magnet is coming closer to the coil, there will be a change in the magnetic flux experienced by the coil that produces an induced current this is the induced current, and this induced current produces the induced magnetic field. This is induced in the coil, and essentially what we're saying that the direction of induced magnetic current, magnetic field shown by B subscript coil is opposite to the direction of the field of the magnet, and that opposite direction is shown as the negative sign. So let me read this. When a bar magnet moves towards the coil, the strength of the magnet's magnetic field, B magnet, increases in the coil because the density of magnetic field lines is increasing in the coil. The change in the magnetic flux due to the magnetic field of the coil induces a current I in the coil, and the induced current induces a magnetic field in the coil. And if we use the right hand thumb rule, that's what will give us the direction of the induced magnetic field. So we have to remember the thumb rule, which was presented in the earlier videos. Thumb rule gives direction of B coil. And that we see that the B coil opposes the increase in B mag. So essentially B coil is to the left, and which is here to the left, and B magnetism is to the right. They're opposing each other. That is what is the Lenz's law. Now I have presented two more pictures at the bottom, and I want you to verify the validity of Lenz's law by yourself in the two images. In this slide, I'm just documenting and writing down a recipe which may be useful in problem solving and trying to find out the directions of induced magnetic fields, induced currents, and induced EMF. There should not be a comma here. Induced currents and induced EMF. Essentially, we're using Lenz's law or the concept of Lenz's law to find out the directions. So first, typically we will have a coil in the problem, a magnetic field, and the area of the coil will be known. So we'll have to see what is happening to the coil first. Is it moving, or is it rotating, or what is happening? And so we'll draw a sketch of the situation, and we'll try to visualize what is happening in the problem. And then we will find out the direction of the magnetic field which causes the change in the flux. There should be a change in the flux to have induced EMF. Once we have the induced EMF, then we can get the direction of the EMF and the current and the field later on. Then we have to determine if the flux is increasing or decreasing. Now, determine the direction of the induced magnetic field. And how do I find that out? The induced magnetic field will be opposing the change in the flux produced by the field. So if, let me write this down, if the flux increases because of the field which is present in the surroundings, then you can expect the field due to the coil, or the induced field, should be in a direction that opposes the change. Opposes the change in, opposes the delta phi. So the directions, so if delta phi is increasing, then the B field will be in such a direction that it is decreasing the flux. Then once you know the direction of B induced, we're able to use the right hand rule to figure out the direction of induced current. And once you know the direction of induced current, you can find out the direction of induced voltage or induced EMF, and you just have to use the concept that current flows from positive terminal to the negative terminal. And once you know the current direction, you can figure out the terminal's direction, which one's positive and which one's negative. That's how you can use the Lenz's law to figure out the directions of induced EMF, induced current, and induced magnetic